Hi everyone, I'm Ziwen, a PhD student from ASCAR Research Group at UCI. Today I will present our work titled Too Afraid to Drive, Systematic Discovery of Semantic Vulnerability in Autonomous Driving Planning on the Physical World Attack. This is joint work from our group and also our collaborators at UCI and UCLA. Nowadays, the high-level autonomous driving vehicles are publicly on the road. Those vehicles can drive automatically without human interaction in most cases. Some companies like Waymo, Baidu Apollo, and GM Cruise are already providing public service even without the safety drivers. Now, let's look into the existing security research in this field. First necessary step in AD system is sensing. In this step, the vehicle will understand the surrounding environment by using different sensor data. Some common components in this step include camera object detection, LiDAR object detection, and also sensor fusion, which will combine the different sensor inputs. We also have prediction, which is used to predict the future trajectories of surrounding objects. Localization is also part of it. It will tell the position of the vehicles by combining different sensor inputs. Unfortunately, prior work have demonstrated that most of the components here are vulnerable to external attackers to a certain extent. However, there are more steps in such systems. There's a planning step which will determine the planning trajectory the vehicle will follow. And there's also a control step which will generate the concrete control command and send it to the real vehicle. A natural question comes here. Can we think one more step ahead from a security perspective? Will the next step, the planning or the critical decision making, also be vulnerable and thus exploitable for external attackers? To answer this question, let's look into the definition of semantic vulnerability in our work. Semantic vulnerabilities are those vulnerabilities that can be exploited by the attackers and leads to unexpected driving decisions in AD planning. To be more specific, let's look into this figure. So we have the AD system with sensing and also planning step. Now imagine there's an external attacker, and the attacker can find a way to manipulate the external inputs of the whole AD system. Those inputs can be further propagated into the planning and trigger some bugs or design flaws inside the planning. Later on, these bugs and design flaws can lead to unexpected driving decisions. One type of such decision could be overly conservative behavior, such as unnecessary sharp braking, stopping, or giving up mission-critical decisions. We focus on this type of behavior since we believe this is more generally exposed in today's AD systems. And also, we refer to them as semantic vulnerability because they literally disrupt the service provided by the AD vehicles. Now, let's introduce our attack target, behavior planning. What is behavior planning? To answer this question, let me open the box of planning. There are usually three sub-steps inside the planning. The first one is route planning. Route planning is in charge of generating the route segments for the vehicle to drive. The next is called behavior planning. Behavior planning will make high-level mission-critical driving decisions, such as collision avoidance, lane changing. The next step is called local planning. In this step, the vehicle will transform the high-level driving decisions into the concrete driving trajectories. And our focus in this work is the second step, behavior planning, because we want to change the high-level driving decisions into unexpected ones. And next, I will introduce the threat model. How could the attacker find a way to manipulate the external AD system inputs? The answer is very straightforward. We directly use some common roadside objects, which can be controlled by the attacker, such as a dumped cardboard box or the parked bicycles on the roadside. Such objects are very common on the roadside and thus make our attack practical and stealthy. The last piece of the problem formulation is the consequences of such vulnerabilities. The first possible consequence is bad user experience. Such vehicles could be used for robo-taxi and also delivery service. The DoS vulnerability will lead to delay and further lead to bad user experience. And also, if the vehicle suddenly stops inside the road, it will raise some safety concerns, which will be demonstrated later in this presentation. And also, if your vehicle gets stuck in the public area, it will block the traffic. And what makes it worse is if it happens in some sensitive area, such as in front of the gas station, it can also lead to law violation. And next, let me show you a demo created with a semantic vulnerability we discovered from Autoville.ai, which is an open source full stack autonomous driving software. So let's look into this scenario setup. Imagine as a human driver, how will you react to this scenario? I believe most people will probably ignore those set objects or slightly slow down because those objects are totally off the road and could not affect the normal driving. And also, this is a heavy off-ramp. It's definitely dangerous to stop here. And also, this setup is pretty common in daily life. Please check out these two pictures I took around my campus. And now, let's look into the video to see how the AutoWheel.ai will react to such scenario. And here is how the attack scenario looks like inside the simulator. This is a heavy off-ramp, and we put two common roadside objects. Now let's see how the AutoWheel will react to this. Now the vehicle is normally driving inside the lane, and it makes a sharp brake and permanent stop due to the off-road objects. Now let's see the safety consequences. Imagine that the vehicle is followed by a human-driven vehicle with a common reaction delay. Now, a real-end collision happens after the vehicle makes the sharp stop decision. The reason behind this is first, there's very limited reaction time for the following vehicle. And also, this sharp full stop decision is totally unexpected in this heavy off-ramp scenario. Now, let's look into the root cause of such vulnerability. Imagine that the vehicle is normally following the lane, and a common car width is 2.11 meters, and the common road width is 3.5 meters. That means there's enough space for vehicle to safely drive inside the lane. Let's see how the AutoWheel will react when there are static objects around. AutoWheel will usually apply a lateral safety buffer, which is 1.2 meters. After applying these lateral safety buffers, the remaining space will become the drivable area. However, in this case, the width of the drivable area could be as small as the road width minus twice the lateral safety buffers, which is much smaller than the common car width. So in this case, the AD vehicle will think there is not enough space for it to safely bypass the objects. As a result, it will make a permanent stop decision in front of the static objects. To systematically discover all the semantic DoS vulnerabilities, we have designed a tool, which is novel dynamic testing tool named PlanForce. However, building such a tool is not straightforward and simple. In this page, I'm going to show you the challenges we met in this system design. Just like traditional fuzzers, we have a planning executor, which will execute the inputs. And also we have an input generator, which will mutate the inputs. We also have a seed selection to determine which input is better in terms of vulnerability discovery. And all these three components form an evolutionary testing loop. And the first challenge is that we have to determine which driving decision is overly conservative. That means we need to build a domain-specific testing oracles. And the second challenge is that we have to generate input that satisfies some domain constraints. For example, we cannot arbitrarily put vehicles or static objects inside the lane. And next, we have to design an efficient feedback to guide the whole testing process. And next, I will show you the solutions one by one. Let me first introduce our first solution, planning environment, or the PI. This is our domain-specific testing oracles. We define the planning environment as follows. Under a given specific planning scenario, no matter how the attacker changes its controlled objects, the desired planning behavior should always be the same. Now, let me use a simple illustration to demonstrate this idea. Imagine that the vehicle is normally driving inside the lane. Usually, no matter how the attacker changes the position of static objects off the road, the vehicle should always do the same behavior. Under some specific case, however, if the attacker can find a specific placement of objects, and that leads to a stop decision of the vehicle, then that's a violation of planning environments. And also that tells a discovery of semantic DoS vulnerability. And also we have expressed the PIs with temporal logic. In our work, we have systematically defined planning environments under 8 diverse scenarios, and also we have formally expressed them. Besides the static objects, we have also described how the moving pedestrians and the vehicles should behave. In our testing system, we have built a vulnerability checker following the idea of planning invariants. And next, I will introduce the domain-specific input generation. We perform a three-step input generation, including static property generation, PI constraint enforcement, and also dynamic property generation. By doing this three-step input generation, we can make sure that all the objects will satisfy the domain-specific constraints and also maintain diversity and inheritance during the whole implementation process. Our last design is called BP vulnerability distance, which is a gray box guidance. Our goal is to reach some unexpected driving decision in the program. To address this, our idea is very straightforward. We want to use the distance between the occurrence in those decision-related predicates to guide the whole decision changes. However, implementing such an idea in the real-world program is not straightforward. Here is a snapshot of a very small part of Apollo land-changing decision-making program. And to address this, we have performed two-stage analysis. We have an offline static analysis. In this stage, we will extract the control and also data dependency from the program. And we will also generate vulnerability distance profile to instrument the program. And also in the online dynamic analysis stage, we will calculate this distance on the runtime. Now let's merge all the design together into the system diagram. So on the left side, we'll have all the offline analysis stage. Once given the source code, we'll generate the control and data dependency and further instrument the program. And after that, we can replace the C selection and also the planning executor with the instrumented one and also a domain-specific vulnerability distance. Now let's talk about evaluation results. We have tested plan files on 3 different BP implementations, including Baidu Apollo and Outwell. Both of them are full-stack open source AD software, and we're able to find 9 previously unknown semantic DoS vulnerabilities. One is caused by program implementation bug, while the others are caused by overly conservative planning parameters, such as safety buffer or angle threshold, or also overly conservative estimation of object intentions, such as pedestrians or parked bicycles. We have tested diverse driving scenarios from 40 driving traces and also 8 different scenarios, such as lane following, lane changing, lane borrowing, and different type of intersection paths. I also want to show a few case studies we have created. First, we have created the lane following vulnerability with a real-world driving traces. On the left side, we can see the setup. This is a real AD vehicle, and we have used 2 static objects on the roadside. And on the right, we can see this will lead the AD vehicle to make a permanent stop decision in front of static objects. We also have a stop sign scenario case study. The attacker can simply put 2 parked bicycles around the intersection, and later this will lead to the victim AD vehicle to permanently stop in front of the stop sign. And we also have a lane changing scenario. The victim AD vehicle wants to change the lane to the left. However, the attacker could use a targeting vehicle to make the victim AD vehicle give up this lane changing decision. And in conclusion, we are the first to perform AD planning specific vulnerability discovery with a domain specific vulnerability definition and also a practical threat model. We have designed plan files, a novel dynamic testing tool. We have demonstrated that plan files can discover 9 previous unknown vulnerabilities on 2 practical open source full-stack AD systems. And we have performed exploration case studies on 3 diverse driving scenarios with simulation and also driving traces practice from a real AD vehicle. Besides, we have also informed 24 companies who is currently developing AD vehicles. And that's the end of my presentation. We also have more demos, more details, and source code release on our project website. Please feel free to visit our website. And thank you.